So now let's consider dipole-dipole interactions. An example of this, say if I have hydrogen fluoride and it has a dipole moment, and you know that there are partial charges, so we have a dipole moment is from the positive to the negative end of the HF molecule. So these dipoles can interact from a neighboring hydrogen fluoride molecule, and you can have the positive end of a dipole interacting with the negative end of a neighboring dipole. And you might wonder why aren't these linear, end to end? Well, there's more complicated things than just dipole-dipole interactions going on. When we talk about charge interactions, we consider dipoles, but if you expand the representation, you have quadrupoles, octupoles. So you also have hydrogen bonding, which we'll look at, and so there's more to it than just the single dipole-dipole interaction. But these dipole-dipole interactions are fairly strong, and they hold molecules together, and water is a liquid because of these dipole-dipole interactions. In line with dipole-dipole interactions, we have hydrogen bonding. Now when you have hydrogen bonded to nitrogen, oxygen, or fluorine, these are electronegative enough that you can have enough charge separation between the hydrogen and these other atoms that you can have something special called hydrogen bonding. And in the water molecule, we have our water molecule here, and you can have an interaction between the partially positive hydrogen of one water with the partially negative oxygen of another water. So this is a direct interaction between partial positive and negative charges through the hydrogen interacting with a neighboring nitrogen, oxygen, or fluorine. So this is an example of hydrogen bonding. In HF that I drew before, you can have hydrogen bonding because here hydrogen is bonded to a fluorine, and so we have fairly big charge separation, and so this partially positive hydrogen can interact through hydrogen bonding with the partially negative fluorine of a neighboring molecule. So this right here, what I've drawn as a dotted line, is hydrogen bonding. Now, DNA is two segments. It's called a double helix, and DNA has the bases here, and these bases are held together between strands due to hydrogen bonding. So the strands, the two DNA strands, are held together through hydrogen bonding between base pairs on opposite strands. So you have a whole bunch of these hydrogen bonds, and so they add up to a very strong force between holding these two strands together. Okay, now let's consider dipole-induced dipole interactions. And what is an induced dipole? Say you have a molecule or an atom that does not have a dipole moment. If you have a dipole next to it or close to it, it can induce a dipole in that atom or molecule that doesn't have a permanent dipole moment. So say we have water, which has a dipole moment, next to, say, an argon atom, which doesn't have a dipole moment. So I'll draw the dipole here for the water molecule. Here we have a negative end of a molecule, a water molecule, and so this partially negative charge is going to repel electrons on this side of the argon atom, and so electrons are going to be repelled, and so you'll have electrons moving to the right side, and so you'll have a partial positive charge on the left side of the argon and a partial negative charge on the right side of the argon atom. So this doesn't happen naturally with the argon atom, but when the argon atom is next to a permanent dipole, then this repulsion between electrons of the oxygen and the argon atom can occur, which produces this charge separation. I'm going to erase the arrow. So this is a dipole inducing a dipole in a neighboring atom or molecule. Now let's consider the weakest of the intermolecular forces, and these are called dispersion forces. And another name, synonym, is London forces. So you'll see both used in the literature and in books. Dispersion forces occur through instantaneous dipoles inducing a dipole in a neighboring atom or molecule. Okay, so say we have two argon atoms. Neither have a dipole moment, but the electrons are moving. And so at an instant, we could have a slight charge separation. And this is just an instantaneous dipole. It just happens for an instant, and then this dipole will collapse because the electrons are moving. In another instant, a different dipole will surface. So here we have an instantaneous dipole. Well, that can induce an instantaneous dipole in a neighboring argon atom, because if we have an abundance of negative charge on the right side of argon number 1, it will repel electrons on the left side of argon 2 and push them over to the right side, and so that will give us a slight positive charge, and so there'll be an attraction between the two argon atoms. So this is an instantaneous dipole inducing a dipole in a neighboring atom. This dipole will then quickly collapse, so will this one, and then another one can be induced just from random motion of the electrons. So these are weak forces, but they exist between all matter. So even things that don't have a permanent dipole attract other molecules and atoms through this instantaneous dipole interaction called dispersion forces. The larger the molecule, the easier it is to distort the electrons around that molecule, and so dispersion forces will be greater for molecules that are larger. So as a nice example, let's consider the boiling point versus molecular weight. So the boiling point gives us an idea of the magnitude of the intermolecular forces, because if you have a liquid here in a beaker, then the molecules, in order to boil, have to get into the gas phase, and so they have to leave the liquid surface. Now, if we have intermolecular forces, attractions between molecules in the liquid, they have to break those attractions to get into the gas phase. And so the boiling point will give us an idea of the magnitude of the intermolecular forces. The stronger the intermolecular forces, the more heat required to break those attractions and get to the gas phase. So the higher the boiling point will be for stronger intermolecular forces. If you look at a series of hydrocarbons, so let's look at a series of hydrocarbons and say we have pentane, hexane, heptane, octane, and nonane. So the boiling point versus a molecular weight will give you about a straight line. So as the molecular weight increases, the number of atoms in the molecule increases, so does the boiling point. You can do this also with noble gas atoms. The same trend will follow with the noble gas atoms. Here we have the boiling point in Kelvin for each element, and helium has a very low boiling point of 4.2 Kelvin. It's just 4 Kelvin above absolute zero. But as we get larger, the number of electrons increases. You can see that the boiling point increases. So we go from helium to neon. We increase from 4 to 27 Kelvin, and we get all the way down to xenon, a very large atom. The boiling point is 165 Kelvin. Now, none of these have dipole moments. This is all dispersion forces. We have an instantaneous dipole in one atom creating a dipole in another atom.